Hi, so I thought I'd make a video series, a short one, on proving the Arzela Ascoli Theorem from real analysis. It's a pretty big theorem, so I think for the first part we'll just focus on proving a lemma that's needed for the proof. So, how does the lemma go? Let Fn be a uniformly bounded sequence of functions on a closed interval AB. Right? And by uniformly bounded, what I mean is that Fn of x is less than or equal to some m for all n and for all x in the domain. Essentially, the bound m is independent of both x and n. It doesn't matter which function I am in the sequence or whatever input I put in, all of that stuff is bounded by the same m. So that's what it means to be uniformly bounded. Okay. Fix a sequence of rational numbers in AB. Of rational numbers. And we call them x1, x2, x3, so on. In AB. Then this lemma says that then there exists a subsequence of Fn that converges at each xi. Converging at each xi. So that means there's a subsequence of these Fn's that will converge at each of these rational numbers in AB. And the way to visually think about this and why we're doing it is, well, here's AB, and suppose my x1, x2, x3, maybe here's x1, there's x2, maybe x3 is back here, x4 is up here, x5, x6, x7, blah, 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 blah. It's a whole sequence of rationals. There's infinitely many. So they're going to dot, and in a way, they're going to sort of fill up AB. What they really are, and what they're really going to end up being is, they're going to be like goalposts, spots where we know we have a sequence that converges at them, and then each of them can have a neighborhood, and the overlapping neighborhoods should eventually cover AB, and that's going to show up much, much later when we actually prove the real theorem. But for now, we'll just prove that there's a subsequence that will converge at each of these xi's. So how are we going to do that? Well, consider the sequence of numbers that's going to be Fn evaluated at the first rational point x1. Okay, so this Fn of x1 is a sequence of numbers. That sequence is f1 of x1, followed by f2 of x1, followed by f3 of x1, so on and so forth. Okay? But because my Fn's are uniformly bounded, certainly this sequence here will be bounded. Therefore, we can use the Bolzano-Weierstrass theorem, which says every bounded sequence has a convergent subsequence. So by BW, Fn x1 has a convergent subsequence. And maybe that subsequence will be like, I don't know, maybe it will have f1, maybe it'll skip f2, but it'll have f3 of x1, maybe it'll skip f4, but it'll have f5 of x1. Yeah. A whole bunch of them. So on and so forth. All right. Here we are. F1 of x1, F3, F5, 6, 7, 8, 9. That's been consecutive, but obviously it's a subsequence, so it can skip however many. Well, equivalently, I could say that the subsequence here of functions f1, f3, f5, f6, f7, f8, f9 converges at x1, saying the exact same thing, right? if this sequence of numbers converges, that's the same thing as saying just taking the f's, that's a sequence of functions now that converges at x1. It's just the exact same thing. And let's call this subsequence fn1. Okay? So what have we just done? We have a subsequence fn1 of our original sequence fn that converges at the first irrational point x1. And that's a good stepping stone, because what do we really want? We wanted a subsequence of fn that converges at every single rational point, x1, x2, x3 forever. We're not there yet, but at least we have a subsequence that converges at the first rational point, x1. And that's a start. So what we have so far, fn1, which consists of, in this case, f1, f3, f5, 6 through 9, and more on, this converges at x1. So now we can actually just do the exact same thing, but to x2, starting with this sequence. So now consider this new subsequence here, fn1. Consider fn1 and now I input x2, the second rational point. So now consider the sequence of numbers, fn1 of x2. It's going to be f1 of x2, f3 of x2, f5 of x2, f6 of x2, 7, 8, 9, so on and so forth. Well, this is also bounded since the fn's are uniformly bounded. Therefore, we can apply the Bolzano-Weierstrass theorem again. And this sequence of numbers will have a convergent subsequence. So, by BW, some subsequence of these guys are going to converge uniformly. Are just going to converge. And, or equivalently, I could say, there exists a subsequence of these fn1s such that it converges at x2. So maybe, and that subsequence we'll call fn2. So perhaps fn2 consists of, maybe I don't have f1, maybe I have f3 now, maybe I still have f5, maybe I skip f6, I have f7, and maybe I still keep f8, f9. So now, this fn2 consists of these guys, and we know it converges at x2 because that's how we got it. We applied BW to fn1 to get the sequence fn2 that will converge at x2. But notice that this fn2 is a subsequence of fn1 because that's where we took it from. So since fn2 is a subsequence of fn1, it also must converge where fn1 converges, which is x1. It also converges at x1. And this is just using the fact that if a sequence converges somewhere, then any subsequence will also converge there. And that's sort of the thing that we're going to use, right? We had our original fn's, and then we evaluated them at x1, used BW to get a subsequence that will converge at x1. That subsequence is fn1. Then we just did it again. We evaluated fn1 at x2 now, the next rational point, applied BW to get a subsequence of that will converge at x2. That's how we know fn2 converges at x2. We made it so. But then, because it's also a subsequence from fn1, it will also converge where fn1 converged, which is, in this case, x1. So now we're just going to do this over and over and over again. So how to write that out? Well, in general, let's use let f and k be the subsequence of f n k minus 1, the subsequence before, obtained by BW applied to f n k minus 1 of xk. Okay, so what I'm saying is, let's say we started with fn k minus 1, the k minus 1 subsequence in our process, so to speak. Then we're going to input the next rational point xk. That will be a sequence of numbers. It's going to be bounded. We'll use BW to get a convergent subsequence fnk, which will converge at xk. Converging at xk. Then we have a nested chain of subsequences, right? We saw this before. The very first one, fn1, contained fn2, which will contain fn3, and this containment will keep on going. The way it was set up, fn1 converge at x1, fn2 converges at x1 and x2, fn3 by the same process will converge at x1, x2, x3, so on and so forth. So you have this lovely chain of subsequences. And now we're getting there, right? But what we need is a single subsequence that will converge at every single rational point. So far, I can just get a finite amount down the chain, and it will converge at all the rational points up until then. But I want a subsequence that will converge at all the rational points. So there's just one more step to go. Right. Take the subsequence of the original fn, so just essentially take a bunch of fn's, but the ones that we're taking is the following. Formed by taking the kth term of fnk. Now, that seems a little confusing. What does it mean to take the kth term of fnk? What is that? It's really best done by just visualizing an example. Let's say fn1 consisted of, now I don't entirely remember which ones I had picked, but it doesn't really matter. Maybe it consisted of f1, I think it had f3, f5, f6, f7, f8, f9, and so on. Recall, this fn1 converges at x1. fn2 was a subsequence of this. And I think I took f1 again. No, actually, I think I started with f3, then it was f5, then it was f7. Maybe it still has f8 and f9 goes on. This one converges at x1 and x2. Remember, it converges at x2 because we use BW to make it that way, and converges at x1 because it's a subsequence of the one that converges at x1. fn3, maybe I will keep f3, keep f5, maybe I skip f7, f9, and so on. What does it mean to take the kth term of fnk? Let's just do it. We'll take the first term of fn1. That's for k equals 1. Well, here's fn1. The first term is f1. So I'm going to take f1. Then, let's let k equals 2. I'm going to take the second term of fn2. Here's fn2. The second term is f5. Third term of fn3, that's f8. And you see what's happening here? I'm getting a sequence of functions along a diagonal-ish kind of line, okay? And that's sort of why this is called a diagonalization argument. You can imagine if fn4 was a subsequence that started at f5 and maybe it went to f9, f11, f12, then fourth term of fn4, it would contain f12. It's sort of going in a diagonal. And the thing is, because I'm taking the kth term of fnk, it's like the next term is going to be further along than the previous one I took. If I take the third function of fn3, I'm making sure the next function I take is definitely beyond the one that came before in the sequence. Because remember, a proper subsequence of functions, the indices have to keep on increasing. The fact that the term I take is going up with the subsequence I'm picking from ensures that that is the case. It ensures the terms I take are always going to be further along than the previous one. F5 is farther along than F1, F8 farther than F5, F12 farther than F8. It's because I'm taking the kth term of fnk. So we get a subsequence of fn this way. And in our example, it's going to be f1, f5, f8, f12, and so on. But by its construction, it's going to converge at every single rational point. Why? Because this subsequence is a subsequence of each fnk. Think about it. It is, because each of these guys are subsequences of the one before, and by taking this diagonal subsequence, it's going to be a subsequence of each of them. Because if you just look at it, it's going to be. You can see this f5 is over here, this f8 is over here, this f12 will also have to be there. The diagonalness of this sequence means it's going to be a subsequence of each fnk. And you just sort of have to stare at it long enough to realize that it really must be true. Therefore, it will converge wherever each fnk converges. Which is, so that means because the blue subsequence is a subsequence of fn1, it will converge at x1. The subsequence of fn2, it will converge at x1 and x2. The subsequence of this, it will converge at x1, x2, x3. It's going to converge at every single rational point because you just keep going down the line, which is each xi. Which concludes the lemma. So, diagonalization is something that, usually in analysis you see earlier on, proving that the reals are uncountable or stuff like that, or clever arguments about surjectivity of functions. But here it is showing up with sequences of functions. So just to recap, we proved that I have a uniformly bounded sequence of functions fn on an interval ab, and I fix a sequence of rational numbers in ab, little dots. Then I can always find a subsequence, a beautiful diagonally formed subsequence of fn that will converge at each of those rational points. Done by having a chain of subsequences, where because each subsequence is a subsequence of the one before, it will converge at all the same points the previous one converged at. Sort of keep doing it.